Bala, are you able to hear us?
Yeah, I'm able to hear.
Okay. Can you share your screen because it is with multiple?
Yeah,
Okay, we'll give few minutes for the attendees
yeah,
as
sure.
we see people are joining in.
Yeah, let's wait for some time.
Sure. Okay. Yeah. Can you go back, Bala, about the community? Few slides.
Yeah.
Yeah. Thank you. Okay. Maybe we can start. Okay. Hello all. Good evening. Welcome to Azure Developer Community and innovation segment. So today we have doing the it's been a long day for us. We thought of doing it and yes, finally today we are doing it. And so here you have two QR codes. So one is for our Azure Developer Community Meetup page, and the other one is for our WhatsApp group. So if you are interested, please feel free to join it. Yep. I will give a short intro about our community, what we are doing. Then I can hand it over to the speaker. Yeah, yes, Bala, you can go to the next slide. Okay. Yeah. Azure Developer Community. We have been doing this for past 3 to 4 years, and mostly we are doing the meetups. So in the COVID time, we were doing online meetups. Then we moved into offline meetups. So every third Saturday, we are having our offline meetups, in-person meetups in Microsoft Office. So mostly we are going theme-based sessions like AI, data, DevOps, security. So if you are interested, please feel free to watch out our meetup page, and we will be posting our events. Even we have scheduled our like 2 months events. So we are giving a platform to network with different people, say beginners, professionals, experts. So we are giving a forum to connect with everyone. For example, college student can come to our event and get some understanding about the technologies, Azure technologies or ML technologies, and he can get the exposure to interact with the industry professional. And we were doing some Azure certification study jams. And in future, if you have any need, please let us know. We are happy to start that again. And we give tech talks in colleges. So if your college having some club and you need support on tech talks or some workshops, we are very happy to do. On top of it, if you are willing to share your knowledge with our community, please reach us. We are happy to host you. Even if you are a first time speaker or women speaker, we will give more preference, and we will give the necessary trainings to that. Yeah, Bala, can you go to? Yeah. I will give a short intro about our speaker, Balamurugan. He's a machine learning engineer intern at Tiger Analytics. He's a Microsoft certified Azure data scientist associate, and he holds a BTech degree from Sastra. And Balamurugan, having experience running student communities in his college, and he conducted lots of workshops. And he's an enthusiast who explores more on the research in NLP. And I like to thank Anjaneyulu who has introduced me, Bala, sorry, who has introduced me and making this event happen. And yeah, once again, thank you all for joining us. Bala, over to you.
Yeah. Hello everyone. First, I'll just share the repository first. Today we are going to discuss about this paper only. Attention is all you need, where the authors are proposing the architecture of transformers. Navneethan will be sharing this link with you all. You can just go through it if you want. And yeah, let's get started. Yeah. First, before diving into the paper and before diving into the Transformers architecture, I'll just give a gist of the process of training, how NLP works, everything. So first, before transformers, we had some sequential architectures like RNNs and all. So those architectures we call it sequence to sequence. That can be used for tasks like translation, summarization, where sequence to sequence means input will be a sequence and output will be a sequence. So normally, if you take translation or summarization, let's take translation. Input will be a sequence of words in one language, and the output will be a sequence of words in another language. So where all that kind of task is there, we can use sequence to sequence architectures. So I'll just show you a normal RNN how the structure will be. Here we can see a sentence, what time is it, and question marks. These are called as tokens. Individual piece of words are called as tokens. It's not exactly, nowadays we are having more advanced algorithms like byte pair encoding and all. It is not necessarily a complete word. Let's see, for simplicity, let's just take it as a word. So this word is one token, time is one token, and each individual word is a token that will be passed as input to RNN. This entire layer is a RNN layer. This entire five cells together is one RNN layer. So what will happen is whenever this first token is being passed, here there will be some mathematical function. For example, if you know deep learning, normal neural networks, just in neural networks we'll have in each cell it will be y equal to mx plus c, right? One bias term will be there, one slope term will be there. Similarly, in RNN also we'll be having some set of functions that is capable of processing the dependency between the words. So for this is the first time step. This is the first word that is being passed, and here some process will take place. And after this, whatever processed here will be passed over to the next time step, so that this can also be processed. So there will be two outputs for each RNN cell. One will be towards the next cell, and one will be the output. This will be the hidden state at time step T1. So to process the time step T2, this needs two inputs. One is the input token, this word time, and the output of output of the previous cell. So to process this particular time step, we need the output of the previous cells. To process this third cell, we need the output of this particular cell T2. So here we can see there is a horizontal dependency. So what's shortcoming? What's the disadvantage of having this horizontal dependency? Whenever we are having this horizontal dependency, we cannot process these words parallelly. To process the last word, this question mark token, we need to process all the words before. Then only we can process this last final word. So that there is a dependency between things, right? So that parallelization is not possible. So processing a large chunk of data, large set of tokens is not possible. It's not feasible with RNNs. It's a kind of a very complex and very time consuming thing. So this is a basic overview of how RNN works. Like RNN will take input as a word, input as sentence. It should be tokenized into each individual word. Each will be passed it to RNN cells, and the output will be corresponding hidden states at each time step. So this is how a basic overview of RNN, and I'll tell how tokenization works. How we will be passing this text directly to RNN? We can't pass it, right? So all the deep learning algorithms, any algorithm, if you take an AI, everything will process only numeric, right? So we can't directly pass this text as it is. So we need to first encode it. Encoding means first I'll just take this sentence. This is the input text. This is a sentence. So this sentence should be tokenized first. Tokenization, for simplicity, now the tokenizer will be normal. We'll be splitting based on spaces. So wherever space comes, we'll split, and each space separated word will be a separate token. So this is, yeah, input and full stop. These are the five tokens that we have, and the CLS and SCP, about that I'll come to that later. These are all called as special tokens. No need to worry about it now. Just take this. This is the input. So each token will be mapped with one ID. That can be, for example, if you're having totally, if you're having a data set of 50,000 sentence to sentence translations, like for each row will be like, let's example take English to Hindi to English translation. So on the one column we'll be having Hindi text, and on the other column we'll be having the corresponding English sentences. So yeah, let's for example, if we have around 50,000 tokens totally in the data set combined together, like whatever word is there, we'll just split it and take it as one set of tokens. And in that, let's assume there are 50,000 tokens. So you will be having unique ID for each token. So you can even take monotonically increasing IDs. So for each word you'll just assign 0, 1, 2, 3, 4 till 50,000, it will be there. So this is how a tokenization process works. Now after tokenization, you can directly pass this number to this RNN cells. But one disadvantage of it is like there is no literal meaning between the IDs, right? IDs doesn't have any meaning, just a mapping. So they don't represent any relation between the words, or they don't represent any meaning about the words. Those are just IDs. So we have one more part called as embedding. So embedding, what it will do is, this tokenization is there, right? After this, we'll be mapping each word to ID. After this, if we take embeddings, what will happen is, each word here, right? Each word will be processed into a vector. So what this vector means, so what type is, this is the words that we have. Each word will be converted into a vector. So what does this vector mean? Here we are taking a four-dimensional embedding. So each word will be converted to a four-dimensional vector, like four dimensions will be there. So after converting it to embedding, these embeddings are just learnable parameters, just like whatever parameters we have in a normal neural network. These embedding layers will also have the learnable parameters. So what does this mean? So after training an embedding layer, what will happen is each word will be aligned together. According to its meaning, or according to the outputs that we decide, output of the model, the tokens will align together. For example, here if we take like after training the model, each word is having embedding, right? Those embedding projected as a vector. This is a two-dimensional embedding. Projected as a vector, how projected as a plot, how it is this fan, light, LED bulb. These four denotes a similar kind of words. These are clustered together. And here, if we take refrigerator, oven, microwave, LG, these are all clustered together. So these represent different meaning or categories of words. Here, if you take these are all related to kitchen, table, sink. So these represents a different meaning, different set of words, different chunk of words. So after training an embedding layer, this is what happens. So after training an embedding layer, each word, instead of just having ID, those words will be converted to a vector which have some meaning about the word, not just simply some random ID. So what will happen after converting words into embeddings? Now it's time to pass the embeddings to the model. So the process you're remembering, right? First, we'll have the sentence. Sentence should be tokenized. After tokenization, we'll be mapping it with IDs. These IDs will then be converted to embeddings. These embeddings are learned during the training. Now these embeddings, instead of these words, this embedding, for example, for simplicity, let's take four-dimensional embedding. But in production, will be if you take state-of-the-art algorithms, mostly the embeddings will be of 512 dimensions or 1024 dimensions, because here we just have a few words. If you take language, we'll be having a lots of tokens, right? So to distinguish between the tokens properly, we need a higher dimension. Two dimensions won't be sufficient. So that's the reason we are going for higher dimension embeddings. So here let's simply take four-dimensional embedding. So what will be converted into an id first, that id will be mapped to an embedding, that embedding, that four dimensional embedding will be passed to rnn. So here in this particular cell, that embedding will be processed, and this will generate a hidden state, and that hidden state will also be passed to the next time step, next rnn cell. This will take in the input at time step t2. This token will be converted to embedding, that embedding will be passed over here. This will take both that embedding as well as the previous hidden state. It will generate some output. Here we are not discussing about the targets. We are just discussing the process of how RNN works. So now I'll just give a gist of how this RNNs are processed in terms of machine translation. So here we are having some Chinese text and the corresponding English text. So what happens here is, this is some Chinese text, right? This encoder is a, layer of RNN, and the decoder is also a layer of RNN. What happens here is, at time step T0, we are having the E naught as the cell, and for T1 time step we are having E1 as the cell. At each time step, what is happening, this particular token will be converted to id, that id will be converted to embedding by the embedding layer. After that, embedding will be passed over to this particular cell, and this particular cell will give its output over to the next cell, and this particular cell will process the input at that particular time step, the embedding vector of that particular token, and the previous cell's output. And this will have some representation of this word as well as the previous word, and this will give its output to the next particular cell. So this will continue till the last. So what's happening over here is, we are getting a representation of this sentence in terms of vectors. So this particular sentence is being converted to vectors by the RNN layer. So that particular output is there, right? So what will happen here, e0 will give one hidden state, e1 will give one hidden state, e2 will give one hidden state, such that we will be having one hidden state for each word. Let's take the dimension of the hidden state as 512, or else let's just take it as 5 as the dimension of the hidden state. So what will happen here is, so what will happen here is, the output of each cell will be a five-dimensional hidden state. That hidden state will be those, like for example, let's take here we have six words, right? So these six hidden states will be combined together. So it will be a 6 cross 5 number of 6 cross 5 matrix of hidden state representation. So that particular matrix is there, right? That particular matrix comprises of the entire meaning of the sentence. Here how the position is being captured, like for example, the word is right in English. That is word is that particular word's meaning changes according to its position. So if you take any language, if you swap the position of the words, meaning will entirely differ. That is one property with any language. So that particular positional dependency is captured by this horizontal sequential dependency. Since there is a sequential dependency, it captures position also. So this is all about the encoder part. Encoder part's output will be a hidden state representation of the entire sentence. That will, for example, here 6 means it will be a five dimensional hidden state. For 6 time step, it will be a 5 cross 6 matrix. So what will happen after that? After that, let's take this. This is the output of the encoder. Let's take this as the output of the encoder. X1 is one hidden state, X2 is one hidden state, X3 is one hidden state, Xn is the nth hidden state. So in our example, we had six tokens, right? So it will be X6. Till X6 we will be having the output, and these will be copied into keys and values. Now I'll explain how attention will be calculated. So these vectors will be copied into keys and values. Now these keys will be now one second. Before diving into it, I'll just tell why attention is needed. For example, here we are getting the output of encoder, right? Now I'll talk about the decoder part. In decoder part, what will happen is we'll be one second. I'll show another block diagram. Yeah, this is better. So here for each time step we are having an input in the encoder side. This is the encoder. This is the decoder. So in the decoder, we are having four time steps. Four tokens are there that will be converted into encoder hidden state. Here we are having a three-dimensional hidden state. So each hidden state will be comprising of three values, three value vectors. And from the decoder side, what will happen? You should be passing the first token. So when translating, what will happen? Encoder hidden state is needed, and from the decoder side, you should pass the first token as input. Using the first token as input, what will happen? The decoder will take the output of the encoder along with the first token. It will try to generate the second token, and then that predicted second token is there, right? That token will be passed over to the decoder again, and the decoder will be trying to predict the third token based on second token and the encoder hidden state so far. So it is an auto-regressive process. Auto-regressive means based on the previous outputs, it will generate the next output. Based on the previous output of decoder, it is predicting the next output of the next token in the sequence. So here one drawback here is how do you know the first token which should be passed to the decoder? Because when training you will be having the pair of sentences, so you know, you take a Hindi sentence and you take a English sentence. That particular corresponding first token in the English sentence that you know from the data set. But if you go in the inference time when you are trying to predict, you won't have that token, right? You won't have that first token. So for that only we will be using some special tokens. I told, right? I'll give some context on this later. So now this will be a start of sequence token, and there will be a end of sequence token. So what does that denote? So the start of sequence token is passed as input for the decoder for every data point. So for every sentence that we are generating, the first token will be start of sequence, so that the model will get to know, the decoder will get to know I'm going to start generating words from this. So the first token will be the start of sequence token. This What will happen here is for the first token, first the encoder part will generate everything. The encoder part will be ready with all the encoder hidden states, and the decoder will be passed with the first start of sequence token. So the start of sequence token along with the encoder hidden state will generate the next token. That next token will be passed to the decoder again along with the generated encoder hidden states. So the third token will be generated. Now another thing is there is one more strategy called as teacher forcing. So instead of passing the decoder predicted output to the decoder again for generating the next tokens, we will be passing the actual ground truth token. Like for example, let's say here we are having some Chinese sentence, and corresponding English statement is knowledge is power. So for example, this knowledge will be passed over to the next for predicting the word is, right? So what will happen, instead of the decoder might predict knowledge as a wrong token. Instead of knowledge, it might even predict something else. During the initial phase of training, decoder won't know what to generate, and it will generate some random things also during the start of training. So what we will be doing, instead of passing that wrong token as input for the generating the next token, we will be passing the actual ground truth token for generating the next token. So the input will be the encoder hidden states that were being generated along with the actual ground truth token for the previous time step t minus one. Now so far I didn't talk about attention. I'm just talking about plain encoder decoder sequence to sequence architecture. So, what is the shortcoming with plain encoder decoder sequence to sequence architecture without attention? So, what will happen is here we are having different, here just we are having four tokens. But if we take real time examples, we might have we might be having more than hundreds of tokens. In that case, what will happen? The token that is being generated right from the decoder side, that particular token does not necessarily be dependent on all the encoder hidden states. That means we might neglect some hidden states, instead of attending to all the hidden states as it is. We might give some attention to places, parts where there is some dependency, there is some actual dependency. For example, if you take translation as an example, within the two statements, if you take one word from the destination statement, like the destination languages statement, for example, Hindi to English means, if you take a English statement, one particular word in that statement won't be depending on the entire sequence in the Hindi statement. It will be depending on only a part of the statement. So how do we look into that parts specifically instead of attending to entire hidden state? That is where attention and alignment scores comes in. So how what is attention? Attention means it's just an alignment score between the words. For example, here if you take two languages are there, here one English statement is there, here I think it's Italian or Spanish something. So here we are having, are you still at home? This is one statement, that is an input. This will be passed over to the encoder. Encoder will have hidden state representation for all these words. Now I am passing the start token to the decoder. Now, after we compute the attention between this particular token and all these hidden states, let's just think of attention as dot product for now, just a simple dot product for now. If you have some context over document similarities and all, for example, if you want to take similarity between two documents, usually we will compute TF-IDF for normal bag of words of that those particular documents. We are having some set of document means we'll be computing the TF-IDF for some bag of words representation of the documents, and take the dot product between the vectors, so that we'll be getting the similarity score between the documents. Similar strategy is approached here. Instead of document level, we are computing it word level. Like we are having the hidden state representation for each word, and we are having a hidden state representation of this particular token from the decoder side. We are having one hidden state representation from decoder side, and we are having encoder hidden state representation. And that particular decoder hidden state representation will be for simplicity, I'll just keep it as dot product for now. We'll be computing the dot product between the two, and that output is there, right? Output will be a similarity score for each hidden state representation from the encoder side. For example, this queries are there, right? This is a self attention, so the query is coming from this tokens itself. But I am talking about cross intention, where query will be coming from the decoder side. So this particular token, right, start token, this particular start token will be made into embedding, and then that embedding will be passed to decoder RNN, and that RNN will generate a hidden state representation for this particular token. And from the encoder side, we will be having these many hidden state representation for each word. Now, this query is a one vector. This is for that start token. This is the output of decoder RNN for that particular start token. That particular token will be computing the attention score between this particular hidden state with the hidden state of all the tokens from the encoder side. Here we are having n tokens, right? For example, here we are having, are you still at home, question mark end. So these tokens will have its own hidden state representation from the encoder side. So that each like for x1 is for end, x1 is for r, x2 is for u, x3 is for still, So xn is for that n token. So we'll be having each hidden state representation for each word. Those will be copied into keys and values. This is the vector that is coming from the decoder is the query, and the tokens, the vectors that are coming from the encoder side are keys and values. So what happens during the computation of attention, cross attention? So this particular one vector query is there, right? This dimension is 5 cross 1. This dimension is 5 cross 4. So what will happen is this 5 cross 1 vector will be multiplied with this particular matrix with the formula QK transpose. So don't consider about the scaling factor for now. We'll be computing the QK transpose first. Q is the query that comes from the decoder side, and K is the key that are coming from keys that are coming from the encoder side. So after computing the dot product between the two, we'll be having some similarity score, some attention score. Attention scores will be there, that will be passed to softmax, so that it will be converted into a representation where the values followed probabilistic distribution. So these values will be from 0 to 1, and it will follow the rule summation of all the numbers will be equal to 1. So these are scaled now, and these attention weights are there, right? We won't take it as it is. Now what we'll do, we'll recompute the output of encoder. We'll recompute the output of encoder such that we copied into keys, right? Similarly, we'll be making a copy of the encoder hidden state into values also. That values will be passed over, and the output there, right? Here we have four vectors, right? Here also let's take for example, here we have 1 2 3 4 5 6 7 tokens are there, right? 7 tokens from the encoder side. So here we will be having 7 vectors of values and 7 vectors of keys. In the attention weights also will be seven values for each vector. So what will happen is we'll be multiplying this attention weights with the values. So this particular value corresponding to this particular vector will be multiplied. Similarly, it will be multiplied with all the values, and instead of just summing up all the entire hidden state representation into one and directly start generating tokens, we are recomputing the output of encoder such that it incorporates the attention score for according to each destination word, each destination token. We are just trying to incorporate. We are just trying to make this encoder's output aligned according to the relation between the destination token and the source tokens. So after computing this, let's take this particular token. This particular token has more alignment towards these positions at home. These are having the highest attention score, and the other places we have lower attention scores. According to that, this the vectors of each token will be scaled. Here we are doing that only. So here the attention scores will be multiplied with the values, and these vectors are being recomputed according to the query, according to the according to the destination token. So after recomputing, we will be concatenating, we will be summing up everything, so that we will be obtaining a single vector representation of the entire source statement. After this, instead of just summing up these sentences and passing it to the decoder, now this rescaled representation of words will be passed to the decoder for the generation. So here we are having, right, this encode hidden states are there. These encode hidden states are passed over. These decode hidden states is coming. This is the query. These are the keys and values are these, and this is the query. Query is coming over here, and this key is also passed over here. Query and key are multiplied, and we are dot product. We are taking the dot product and computing the attention score that is passed over to a softmax function. and that softmax function's output is being multiplied with the values. This will be copied into two, right? I told. So here we are copying into keys, and here we are copying into values. This we have values. The softmax output is being multiplied with the values, and finally for each time step we are following the same procedure, and the entire representation, the entire vectors are just added together to obtain the final context vector. Context vector means the representation of the input token, input statement. So this particular context vector, recomputed context vector, will now then be passed to the decoder. Now the decoder will be able to generate based on the attention to particular parts of the sequence instead of the entire source sequence. So this is the research that research is saying that this particular procedure of calculating attention score is improving the training to a large extent. And also this teacher forcing, I told, right? Teacher forcing means instead of passing the whatever output is generated by the decode, because during the initial training phase it will be generating some random words instead of generating the correct token. Instead of passing the decoder's output to the next to predict the next token, we will be passing the actual ground truth token from the data set to the next to predict the next token. This particular teacher forcing procedure improves the training time by a lot. So that's all about sequence to sequence architecture. So what will happen? You can see a GIF here. Encoder hidden states are being calculated. Then these are computed, and this decoder hidden state is also being computed. And a score is computed between encoder hidden state and decoder hidden state. Then it is passed to softmax. Then again that softmax function is being passed to another function where we are multiplying the encoder hidden state and the softmax. Finally, these are added together, and this addition output is being passed to the decoder for generating the next time step. So this is all about sequence to sequence. Now I'll give a recap of what are all the shortcomings of this sequence to sequence architecture. So here we are having sequence architecture. If you see, look into it closely, both encoder and decoder are making use of sequential architectures like RNNs. One limitation with sequential architecture is for computing values at, for example, here we have the hidden state for time step 3, right? So for computing the hidden state representation at time step 3, we need the hidden state representation at the time step T2 and T1. So there is a horizontal dependency, time sequential dependency, which makes it impossible to parallelize it. So for computing the encoded hidden state at time step tn, we need all the previous hidden states at before the time step tn. So that makes it impossible to parallelize, and that makes the architecture very weak in terms of time complexity. It will take a very long time compared to transformers architecture for generating things, and for learning also. It is not that much efficient in terms of time complexity. So now I'll move to transformers.
Okay.
Now, yeah,
Bala, so maybe
yeah,
if you can show the paper and you go to the flow so that it
yeah,
can
sure,
be. And maybe
yeah,
to add, so we have some limitations in RNN, recurrent neural network. So
yeah,
with the help of transformer, we are addressing the limitations. And also in it, how the attention mechanism, the self attention is happening, and the role of Corey key value QKV. So that also he has explained so far. Maybe if you could show the paper and just go through it, whatever you have.
sure,
Yep. Thank you.
yeah. So this is the paper that I'll be explaining after the section of transformers. So the paper topic is attention is all you need, where they are replacing all the sequential dependencies by using parallel mechanism and attention layers. So here we can see the model architecture, and then they are explaining about how the encoder is, how the decoder is, and encoder is a block n blocks of this one, and decoder is n blocks of this one. I'll explain about it in detail, very detail. Now I'm just giving a gist of what are all coming up. So this encoder, same like sequence, we'll be having one encoder and one decoder. Encoder will be generating some context, decoder will be decoding it one by one by autoregressive procedures. So the entire process is same, but the entire architecture is different. In transformers, everything is parallel. Nothing is there is no time sequential dependency. There is no processing of time step, each time step and going forward. We'll just compute all the tokens parallelly. And if you take here encoder decoder, they are introducing two things: scale dot product attention and multi-head attention. Like I have explained the overview of attention so far. I'll deep dive into the mathematics behind it now after some time. So they are introducing scale dot product attention and multi-head attention. So scale dot product attention. Okay, I'll dive into it later. I'll just go through it
Sure.
first. So
Maybe
you can see,
maybe
yeah,
one more question. So you are reading more research paper. So you can tell the audience. So when you are reading a newspaper, sorry, when you are reading a research paper, so what items you focus? So say I want to read this paper
yeah,
within
yeah,
30 minutes. So how you will
sure,
address it?
yeah. So whenever you are starting with reading a research paper, you should read the abstract and introduction clearly. What they are trying to propose, what is the novelty behind it, and later in between parts you just have to skim through it first. Like you should just get an overview of what is there. Like in this paper, if I take, I'll first read the abstract carefully. So they are telling that. Sequence transaction models are based on complex recurrent so they are telling about a new architecture transformer based solely on attention mechanism. So this is the novelty that they are bringing in. And I'll read the introduction carefully. After that, what I'll do, I'll just go through the paper and find out that they are having a block diagram of the architecture, right? This I'll look into it carefully. I won't read the text much. I'll first in the first flow, I'll
Nice.
just go through everything. They are telling about encoder, decoder, the same thing that was there in the previous works. And scale dot product, I'll be looking into new terms which are there in the paper, like scale dot product attention, multi-head attention. These are some new things that is being introduced into the paper. So at the first flow, I'll just note down, I'll just keep in my mind what are all the important things that I should focus on when I'm reading the paper thoroughly. So I'll read into these particular sections carefully, and these things and all just normal things. And later these parts and all you should be careful. And this training hardware scheduling and hardware schedule optimizer regularization, these and all you can focus on it somewhat. That is it doesn't need that much attention regarding the hardware part. Maybe if you are trying to replicate it, these parts are necessary. But if you are just trying to learn what is new, no need to go through this part that much. You can just skim through it. And this results part, you can get to know what how well this particular novelty is outperforming the other things. Like for example, if you take any ml research papers, there will be a table similar to this where they are listing out previous models and the current architecture that is being used. Here the score being used is blue score. Blue score is a representation of the how well the generated sentence is similar to the actual output. So here we can see that transformer is overperforming the existing architectures. So this particular part you can get to know about the comparison. And you'll be having the conclusion part is also a very important part where they are telling about what they have what they have achieved by using this paper. And after that, in this paper there is no section for future works. In most of the papers, if you see, you will be having future work section. So if you are reading a recent research paper or you want to do some research, after going through a paper, you are getting inspired and you want to continue on that research, there will be a future works section where you can go through what the authors are proposing to be done next, so that you can think in that way also, like what we can do after this, after transformer architecture, what are all the enhancements that I can do in this architecture. So that's all about reading research papers. Once you are reading 4 or 5 research papers, you will gradually get it. So okay, I'll now
Yeah,
dive into the architecture of transformers.
sure.
Yeah,
Thank you, Bala.
yeah. So let's take a basic architecture of transformers. Here you can see input embedding, that is same as I explained previously. Learnable set of parameters which are capable of aligning the words according to the meaning. I told right, if you remember this graph, the embeddings will align the words according to its meaning, or the output. It depends, not necessarily meaning, it will have some internal relation between the words. It will keep some relation between the words. So this embedding layer is same. The embedding dimension that they have used is 512 in the paper, in the attention is all you need paper. They are using embedding dimension of 512. So what is happening, this 512 tokens are there, this 512 dimensional embedding is there. Inputs will be similar, like whatever we have seen previously. For example, if you take this statement, are you still at home, question mark, and this entire statement will be passed. This will be same procedure, tokenization and embedding layer computation. The sentence will be tokenized and the embedding will input embedding to it will be converted to IDs. That IDs will be passed to embedding layer. In the embedding layer, it will generate 512 dimension vector for each token, and we are having positional encoding here. This is one important part that I'll explain so deeply soon. Why we need this positional encoding? So far, if you look into RNNs, we are having this horizontal dependency. So using that horizontal dependency, this encoder is getting to know about the position of words. Like for example, to compute the hidden state at time step t3, we are taking the output of the hidden state, output of the time step t2, right? So there is some sequential dependency. If you look here carefully, we can see the information of previous words getting into the next hidden state representations using the colors. So this is what happens when using a sequential network like RNN. So it will automatically it has the capability of understanding the position of words. Based on the position, it can learn. But if you take transformers, there is no way of understanding the positions, since everything are parallel. So to incorporate the position information, we'll be using positional encoding. I'll get into the positional encoding part later. For now, just think of it as another kind of yeah, encoding layer which incorporates the position information into the vector. So the positional encoding's output will be again a 512 dimension vector, same as input embedding. This embedding will be added with the positional encoding, and both together comprising of the semantic meaning of the word as well as the position, by using embedding and the positional encoding layers, will be passed over to the encoder block. Encoder block comprises of multi-head attention. Within multi-head attention, we'll be having multiple scaled dot product attention, and after that the outputs will be passed over to addition and normalization. So here we are having a skip connection, right? From here you can see the inputs being passed to multi-head attention, as well as there's a skip connection, residual connection, which is directly passing the outputs to addition and normalization layer. So why is the reason of the residual connection? Because after computing the attention, here and one more thing, here you might have the doubt. So far I was just telling about attention between the query keys and values, and queries comes from the decoder side, and the keys and values comes from the encoder side. So here we are just taking everything same, right? So that doubt you might have. This is called as This is called as a self attention, and the attention that was I was explaining, that it was cross attention. You can see cross attention over here between encoder and decoder. This is cross attention, and this is self attention, where keys, queries, and values, everything comes from the same set of tokens. So here I'll explain about this attention part clearly later. Now I'll just give the overview. So this particular values, right? These particular values are passed to the attention, and based on the attention between the words, it will give some output vector. That output vector is added and normalized with the direct raw inputs from that positional encoding layer. The output of the positional encoding layer is having a skip connection directly, and that is being added and normalized. So why the skip connection? This residual connection, this residual connection is important because after this multi-head attention computation, we shouldn't lose the positional information, and as well as the input, whatever the meaning that was given by the input, we shouldn't lose it completely. That's why we are using this residual connection, so that the input meaning will be preserved, as well as the new representation that is learned, that is generated, will also be added to the added further during the processing. So after this particular part, we are having a normal feed forward network. This is a uh, normal deep learning, normal neural network layer, feed forward layer, linear layer, and then this here also we are having this skip connection, right? Wherever we are having this skip connection, that is the reason behind it. We need to preserve the meaning, as well as keep the new representation. We don't want to entirely throw away the previous representation and get the new, but we should incorporate the new information with the existing information. That is why we are having this skip connection everywhere. So this is about the encoder part, and after this encoder part, this is one particular block of encoder. We are having six such blocks in the original paper. This particular block will be replicated six times, and after that, from the final encoder, the output of this will be passed as keys and values to compute the cross attention. Before coming into this part, I will move into the decoder starting part. Here also same, like we will be passing the tokens. First, we'll be passing the tokens to the decoder part in autoregressive manner, as I was explaining in the sequence to sequence network. So how it is happening is, we let's take some particular token, and not some particular token, not random token. We'll be taking the start of sequence. I told, right, some special tokens will be there, so that during inference that will be helpful in generating. So we'll be taking the start of sequence token. That particular start of sequence token will be passed over to here, and the entire context representation will be passed over to here as keys and values. So this particular token, right, this particular token, for the initial token, we'll be having only one vector, so this doesn't have any meaning. The self attention doesn't have any meaning, and after that, the output of that particular one vector will be passed over to this cross attention part, where the process takes place similar to what I explained here. So queries will be coming from the decoder, and the keys and values will be coming from the encoder. We'll be computing the dot product between the queries and keys. We'll be obtaining a representation that will be passed on to the softmax. That softmax function will give some outputs. That particular outputs will be used to scale the values, which is same as keys. We'll be multiplying it and concatenating, and then adding it, and we'll be obtaining a final representation that will be passed to feed forward network. That feed forward network, later we are having the additional normalization, and then that will be passed over to the linear layer. This linear layer is responsible for computing which word, the probability distribution of the next word. So this linear layer will output something that will be passed over to softmax layer. Softmax layer will convert that linear layer's output into a probability distribution for each token. So whichever token is having the highest probability, that will be chose as the next generated word. Now the process will continue. Now I'll explain for the second word. For the second word, from the second word, this particular part will make sense, because what is happening is, after the first word is being generated, the we'll be incorporating teacher forcing. So we'll be taking the actual ground truth token for the first time step. That that particular word will be passed over here. So the startup sequence token and the generated token, the ground actual ground truth of that particular token, SOS and startup sequence as well as that particular token will be passed over here. Here we'll be computing the self attention. So we are calculating the self attention for between the words which are available so far. So we'll be giving a more representative form of the decoder outputs. So we'll be computing self-attention between all the words that are generated so far, and that will be passed as the query instead of directly just a last particular token. So here, from here, this encoder keys and values are coming, right. These will be we will be calculating cross attention between the context representation of this particular part and the keys and values that will be passed over to the addition and normalization layer. So again, the same process takes place. After that, we'll be passing it to feed forward, add, and norm, and then the linear layer it will come to, and this linear layer will be generating the representation for the next particular token that will be passed it to softmax. There it will be computed, that there it will be converted into a probabilistic distribution, where the highest probabilistic token is chosen as the next word. So this process will takes place continuously till when? That is the question now. So we had one issue with the start of sentence token, right? Why we need the special token start of sequence. So the starter sequence is used
Bala,
to give input. Yeah,
sorry to interrupt. We have 3 more minutes, so maybe we
yeah.
can.
Sure, I'll go through it first.
No problem. If required, we can continue one more session also, because I believe we have more content to cover, right?
I think yeah, we
Yes.
have
Yes.
around 20 minutes of content.
Yeah. So we can have one more session. So maybe this architecture you can complete it, and we can take some questions, and we can close it. We can have one more
Yeah, sure.
session.
Yeah,
Thank you.
sure, sure. Yeah. So here we are having these outputs, right. This is passed over to the linear layer, and the softmax functions being computed. So that will give you a probabilistic distribution of the tokens. From there we'll be picking the highest probabilistic token as the next output. So this is what will happen in a auto regressive manner. uh, Navneet, can I continue with attention computation, or can I stop here and we'll take it in the next session?
Yeah. Maybe we can stop it, and we can open for the questions,
Yeah, yeah, yeah,
because
sure.
in
That's better.
another
Yeah, I'll
India
dive
and
into attention deeply. Yeah,
South Africa match also there. Let's not stop
yeah, yeah,
our
yeah,
audience.
yeah,
Yep.
yeah, yeah. Sure, sure. Yeah.
Okay.
Now, anyone, if you're having any questions, you can just ask.
Yep. Please post your questions in the chat. We are happy to answer. And so this is our speaker's profile. Feel free to connect with him. Maybe I will ask few questions, Bala. So
Yeah, sure.
earlier days we used to get very less research paper, but
Yeah,
nowadays even every week n number of research paper is coming. So how can we
yeah,
pick? So which one is needed? For example, this transformer, this paper is very important after the chat GPT era. So everyone wants to understand the GPTs, so how it is handled. Then people started. So how are you
yeah.
following it?
I'll mostly be updated using reading blogs and listening to meetups, and mostly it's based on blogs and news articles. Like every day nowadays, every day, each and every day, we are seeing news like this model has overtaken this one. So this is more reliable and more accurate. And in terms of ethics, this model is more giving more privacy. we have trained it in a ethical way, that we can get some news every day, right? So based on that, whatever model is overperforming, what is happening in the industry, I will just read blogs regularly. Those blogs will give me updates, and later in the blogs they will be mentioning about the models and new things, right? That I'll dive into reading the articles, research articles. That's how I update myself.
Okay, got it. Thank you. Maybe I guess we don't have any questions.
Yeah.
Yeah, Kishore is asking, share the blogs which they can use for learning about these topics. And one question from Bharani, how this is different from
Yeah.
MLM?
How this is different from
LLM.
LLM?
Yeah,
So this is also kind of LLM architectures are based on transformers only. It's not a
transformer.
different thing. Yeah, it's not a different thing. So LLMs are also transformers. So we'll be having some difference in small things in the architecture, some novelties here and there. But the encoder decoder part, like if you take ChatGPT for example, ChatGPT or Cloud, they are all LLMs, right? So they are also having Chat GPT is a GPT, generative pre-trained transformer. That is a encoder decoder transformer only. So we'll be having the same encoder, same decoder, everything will be same. Maybe we will be having some more layers of encoder, some more numbers of encoder, and in between we'll be having some differences in mathematics. In between they will be adding some complexities or adding some novelties. So there is no, it's not a different thing. Transformers are this paper is a basis for all the transformers, all the state of the art um, LLMs nowadays. This paper is
Yes.
the base for everything.
Right,
It's not a
right.
different thing. Yeah.
Okay. Okay, thank you, Bala. I guess Bharani got your answer. And Kishore is asking, is it possible to share the blogs or meetups? They can use it for learning. Like you said, you will
Yeah,
read
yeah,
blogs to get the papers. So
yeah,
if you have something, you can
yeah,
share it in the chat.
yeah. Sure. You can connect with me in LinkedIn, and you can
Yeah,
ask
sure. You
questions
give it.
there.
Sure.
Like I will share it in LinkedIn.
Okay. Thank you. Okay, maybe we come to end of the session, Bala.
Yeah,
Okay. Thank you, Pragya. And yes, we plan to continue this session in our next event. So we haven't planned anything, but we will plan it in another 1 or 2 weeks. And also, you please add the papers. So what are all the papers you want to discuss in our community? Please post it. So we will get it arranged. And even if
yeah,
you have some questions after the session, also please post it in the YouTube page or post it in our WhatsApp. We are happy to answer. And Bala, thank you for spending time and getting the presentation ready and sharing it with us with a detailed explanation and very detailed explanation. It was very good, and I look forward for the next session.
yeah.
Thank
Sure,
you,
sure. Thank you, thank you.
thank you,
Thanks
thank you
everyone.
all.
Thanks everyone for attending. Yeah.
Yes, Barney, you are right. Same architecture only for multimodal as well. So that's where we picked this paper. So like people who wants to talk about LLM or anything, so they will ask to read this paper. So and also it will be easy for us to explain it. We will pick more papers in the future. Once again, thank you all, and enjoy with
Yeah,
enjoy the match, and happy weekend. Thank you, Bala. Bye.
yeah. Thank you, thank you.